Okay, good morning, everyone who's present. I think now I see only Aniruddhan. All right. So let's wait for a couple of minutes.
Good morning, sir. How are you?
Yeah, fine. And I suppose you got that write-up, no? That notes.
Yes.
Person process 7.
Yes.
So today I am not going to start anything new. Basically, just tell you what that thing, that write-up is about. You can, I suppose you are having that thing with you.
Yes.
Yeah. So in that, we were just continuing with the birth and death processes, and many things in that write-up are certain results stated without proofs, because quite a few proofs, I think they use tools which are beyond the scope of such an elementary course. So one can perhaps look into Carlin and Taylor, the appropriate chapters and things like that. And also things might be scattered. Some things may be in a later chapter and so on. Or some other books which are more advanced. So our sort of objective there is, of course, we first to start with, we define the holding time for every state and showed that under one assumption which can be proved by more advanced things. We showed that the holding time for every state has an exponential distribution with the parameter that lambda I plus mu I. The proof is very similar to what we had done for continuous time Markov chains last and the week before. So anyway, for the sake of completeness, I had given a proof. The thing here is that the parameter, of course, depends on the state. Okay. After that, see this kind of holding time is, remember, a basic property of that. That is the time where a Markov chain, like birth and death chain, continuous parameter, etc., they change state. So this is going to be useful in defining a Markov chain associated with the continuous parameter Markov chain, yeah, discrete parameter chain. So that is the let's say the reason, and also how that discrete time Markov chain can be used to get hold of certain asymptotic properties of the continuous time Markov process. Now, basically, that Markov chain, it sort of carries the information concerning the randomness, because in between it basically is going to stay a constant. So the randomness basically comes from there. So therefore, the asymptotic properties which depend on randomness, so we will give just this thing with recurrence and transience and so on. So that is the idea.
Here the way I'm thinking of this is that the Markov chain essentially captures where the xt is without paying heed to the time, right? So if I treat tau n minus tau n minus 1.
You are absolutely right, without paying attention to where the time is, except that that should not be that holding time. That is the where the things change occurs.
Yes. So each holding time is treated to be as 1. And
something like that. Yes, you are precisely that. That's what is happening.
Okay.
So only thing is, some care is needed say for example, in the discrete time Markov chain, the we could take the hitting time as, let us say, infimum t greater than, I mean, n greater than or equal to 1, because that is the time when we want it to be coming back. Now, that is, if in time 1 itself the chain comes back, that is allowed. If starts at, let us say, y, and at time 1 also it is at y, it has not changed state. But since the time is a discrete parameter, that would be counted as one visit. Okay. Whereas here we have to be a bit careful. So if it is the starting point, say that is, we would like to define the analog of rho xy, which we had seen in that discrete time process. That is a process starting from x, visits y at a strictly positive time, right? Here, that strictly positive is not going to be quite informative. So, or rather it could lead to certain anomalies. So, in the definition of that rho xy, especially, remember, many things depend on the this thing, the term, I mean, or this thing rho yy or rho xx. So there some care is needed. So if it starts from y, then you can take it as a kind of a return time greater than or equal to that thing. If it starts from another point, then first time it comes to this point, you have to sort of ignore sometimes. So like that, there are those. If you see the notes, you will see the exact. This is given on, I think, the page 4 of this. See the definition of rho xy. So, for example, in that case, the term t sub y, when it is not, if the initial point is different from 0, it is just taken as the first hitting time. Because, yeah. The starting point is different from y. But if it is x is equal to y, then one has to take it as only the first point or first time point after greater than or equal to t1, where xt equal to y. xt1 would be, or rather x tau 1 would be different from y. That is the reason why we are putting in that definition of ty as infimum t greater than or equal to t1. So there is a subtle sort of difference. So whereas the discrete time, if you take n greater than or equal to 1 and the infimum, then that serves the purpose. So in that way, one gets hold of the Markov chain, and it involves some, after that, some work to, after defining these things, that crucial equality, which we have denoted by spade suit on page, at the end of page 4. So that is the key to the study of certain asymptotic. So since this here, this the superscript H denotes for the thing concerning that discrete time process Hn. And remember in this, in our this thing, the continuous time Markov, or rather the birth and death process we are considering, we are considering only the one-sided process. That is, one-sided in the sense that it taking value on 0, 1, 2, etc. And at 0, what we are imposing is what we have seen in the earlier things as a reflecting boundary condition. So it can be proved, of course, that will be an exercise also for you when I send you the problem sheet, that that HN in this case turns out to be the birth-death chain, discrete parameter birth-death chain with fully reflecting boundary at 0. And for that Markov chain, we had studied the asymptotics last semester. So this that equation at the end of page 4, that spread suit rho xy is equal to rho super h xy, that enables you to sort of easily show things like irreducibility carries over, rather that if and only if recurrence carries over, and so on. Similar thing can also be asserted concerning stationary distribution and so on. I have refrained from doing that because there the rho xy or rho super h xy may not give complete information. Something more you may have to sort of look at. So that I didn't want to burden. So that also can be done. A few years back when I taught that, I also did that, but I was not quite satisfied with that. And this time, since the course is also open to non-math students, I thought I would be more careful.
A small question concerning the non-explosion hypothesis. So the idea is that we want the steps, that is Hn, we want the n to go to infinity, correct?
Yeah, that's asymptotic mean n going to infinity. If the non-explosion condition is not there, then that at some that the point after some point that tau n will not increase. Right? It will be finite. Tau n, let's say tau n, it explodes. That means tau n is equal to infinity, which means the stage tau n plus 1, since the way we have defined it is that if that explodes, that means it never reaches or never changes state. In this case, you have to, I mean, that is what this means here, right? Because if, let us say, tau 3 is infinity, tau 2 is not. So since tau 2 to tau 3, the process is supposed to sort of be staying at the same point, that becomes an absorbing state. So just take the case of even the discrete time Markov chain. If once it is absorbed there, afterwards it doesn't change state. So if you consider the next change point, then the holding time at that is sort of infinity, which means it is a absorbing state. And for absorbing state, the recurrence transience property is uninteresting, right? Because you know that's an absorbing state. There, the interesting thing to calculate is the probability of absorption. So that also one can do using the tools which one had seen earlier concerning probability of absorption and so on. Yeah. And then we had just given two examples. There will also be some problems concerning the pure birth process. Of course, the Poisson process, homogeneous Poisson process is an example of that. So in this case, since it is one-sided like this, one can sort of recursively get hold of an expression for the PIJTs. As you can see, the last line on page 5 indicates. Because it involves solving fairly elementary ODEs recursively, of course. By the way, even this birth-death process, it is two-sided. That is, it is taking value on Z or Z, entire integers. Then the theory is not at all simple. You can look up that the concerned chapter, I think, I don't know whether chapter 3 or 4 in Carlin Taylor first course. For example, in this case, one can recursively solve and get the solution. And in the Poisson process case, we could also do that easily and so on. See, for example, these things we had seen as the solutions for forward equation and backward equation, these PIGs. They solve that equation. Now, whether there is uniqueness and things like that for the system of equation, those are not very simple questions. And also, since it is an infinite space, the sense that the time varies to plus infinity and minus infinity and so on, you also have to be worried about the PTs or the PIJTs going off to infinity in finite time, or rather getting unbounded. So in some cases, there may not be uniqueness, if even in some fairly simple case, if there is no uniqueness, but still the process, defining the process might make sense. And in that case, what kind of solution you should choose among the solutions, various solutions for that system of differential equations. There is something, some concept called minimal solution and so on. So differential equations is a vast ocean. Especially if you are going to deal with a space which is not bounded. So those kind of things, whereas probabilistically so things which are unbounded solutions of that kind of equation, which is supposed to describe probability of certain things, are rather useless. So there are a lot of subtle things involved here. And the last example is a simple thing concerning what is called a MM1 queue. That is, customers arrive according to a time homogeneous process, and there is only one server, and the service time is exponential with certain parameters. So with the each new arrival, the length of the queue increases by 1, and at the completion of each service, the length decreases by 1. The state of the process is the length of.
What is the terminology here? What is MM?
See, M is for Markov. Okay. So the customers arriving according to a Poisson process means the inter-arrival times are exponential. And as you know, exponential distribution is closely associated with Markov property, right?
Yeah. Okay.
The holding times are exponential. And the Markov, it is if and only if the holding times are exponential. We had seen one way proof, the other way is slightly more involved. And the service time is exponential means if you consider just the service testing process, that there will be, you will find a Poisson nature and or Markov nature. And certain things which we had seen earlier can be classified as M/ or M stroke G stroke something. For example, in soon after starting that non-homogeneous process, we considered one thing where people arrive at according to a Poisson process, and the service time is G. The distribution of that is G. And then we consider certain, and in that process we derived certain two processes which are independent and things like that. So that would be an example of where there were the number of queues were infinite. Nobody has to wait for any service. As soon as the new arrival, that thing comes. So that can also be represented as M/G/infinity. G means general.
One is simply the number of servers.
Pardon?
And one is simply the number of servers. Right?
Number.
Okay.
There are also MMQ, K process, K servers, and so on. Then there are things like whether there is only one waiting line where the first come, the person on top of the queue joins, or rather when one counter becomes empty, or there are K queues and things like that. Anyway, so that's an interesting subject with a lot of variations. It's a vast subject by itself. And the telephone technology was the kind of that became, what is it? The initiator of this line of investigation, queuing process. The number of calls coming into a telephone exchange and things like that. How many operators are there to handle the calls? Because even about maybe about 80, 90 years back, telephone calls had become fairly numerous in Western countries. I think at that time, Europe.
Coming back to the non-explosion hypothesis.
Mm-hmm.
So in one of the places you had said that if the birth rates is at most linear, then we will get non-explosion. So
That is a thing which can be proved.
yes.
But
So,
birth rate is more than that, it can explode.
so sorry.
If birth rate is not linear, for example, even if it is quadratic, things can explode. I mean, explosion in different contexts may have different meaning. Okay, here it is in certain certain context it is a absorbing state. In if it is a continuous time process, but not it is non-constant. Let us say even before between jumps. Okay, or it is a purely continuous time, continuous state space process. We will see from the next class, an example of that is a Brownian motion. Okay, that's the here, for example, so far the state space has been a discrete space, right? In the last semester, it was just a discrete time Markov chains. So the time space as well as the state space were both discrete. And now what we are seeing is a case where the state space is continuous, the continuum, and the time space is continuum and state space is discrete, countable. Like what we have seen here, the birth and death thing is, it is, we consider one and only one-sided. So it is 0, 1, 2, etc. Or at best, you can have it as Z or Z, integers. It can also be R or Rn. In that case, explosion can have the meaning that as let us say t increases to 10, the process xt may be approaching infinity. So that is called, that is why the term explosion, it explodes. So there again, for more general processes of that nature, for non-explosion, a possible sort of popular sufficient condition is certain coordinates growth should be at most linear. That is, they are bounded or linear. So boundedness, coefficients being bounded is included in linearity. That is why that A plus BI. B is 0 means it is less than or equal to A, so that is bounded.
Even if a non-explosion hypothesis is assumed, I think it is still possible that tau n will be infinity can be infinity for some n.
That is why this is absorbing state.
Yeah, so but it is possible, right? Because I was kind of thrown off by the note soon before you defined the first hitting time and first return time.
What is it? No. Which page is that?
So
yeah,
the last page, last line of page
3, right?
Yes.
Yeah. So
even if we assume the non-explosion hypothesis, it is still possible that tau n of omega can be infinity for something, right? In which case the Markov chain will be absorbing.
Yeah.
Okay.
So what is your doubt?
Yeah. So that is one. No.
Yeah. I mean, because of the nature of the process here, this explosion this becoming infinity in this case is tantamount to the process getting absorbed wherever it was at time tau n minus 1.
So my only confusion was in that. So even if we assume non-explosion hypothesis, that is non-exclusion hypothesis is true, even then it is possible that we get an absorbing Markov chain.
No, then you will not. No? If it is absorbed, let us say tau 2 is finite, tau 3 is infinite, right? All the sample paths omega for which tau 2 is finite are going to stay on at x tau 2. There may be some sample paths for which tau 3 may be finite. We are not saying that the probability of, I mean, if this thing is not this thing assumes, for example, somewhere we are say, for example, this condition we are assuming with probability 1, right? Where is that? Yeah. So this probability is 1. That means for almost all sample paths, this holds. It is finite. If the negation of this is that this is strictly less than 1, which means for some omega, probability of explosion could be positive. So for such sample paths, the thing gets absorbed. That is how it has to be interpreted. The probability of absorption may not be 1. There are certain states which may be absorbing, but certain states may not, or if there are, let's say, more than one absorbing state, some guys might get absorbed at one state and other people might be at another.
Okay.
It is maybe partially absorbing. Right, like that. Yeah. Okay. Also, I wanted to show something which some object which I might include in the problems. So I think I will share the screen so that you can see it. Can you see?
The screen or the camera?
Wait. I don't know how to make it big. And
Yes.
yeah.
Yes, you need not share your screen. With camera it is.
Yeah, can you see that now?
Yes.
So this add so that the background. Yeah. So XT is your process. Is this clearer now?
Yes, sir, it is better. Yes.
Then you form a matrix, infinite matrix, okay? That is, the number of rows and columns are infinity. But this corresponds to, let's say, the state 0. This corresponds to state 1. And so the first row is minus lambda 0, lambda 0. And the second one is mu1, then minus lambda1 plus mu1, then lambda1, like that. For example, each row, the row total is equal to 0. Okay, then this goes on like that. In each row, only except the first row, only the things corresponding to, let's say, pii minus 1, pii, pii plus 1, they are non-zero. It turns out that these terms are the derivative of Pij t at t equal to 0. If the Pij t's are differentiable for every t, and also let's say the limit as it comes to 0, differentiability at 0 is also P as 0. Okay. So now one can do a similar thing concerning the PIJTs also. You form a matrix PT, which consists of all the PIJTs, I and j varying over from 0, 1, 2, etc., varying over the state space. And take P0 as the corresponding identity matrix, that is all the things which one on the diagonal, main diagonal. So in that case, the backward equation can be viewed upon as the A multiplied with P T, that is P prime T, that is the derivative of P prime T, derivative P prime T is equal to A P T for T positive, and at P0, that initial value is identical. And similarly, the forward Kolmogorov equation can be expressed as basically the same thing with the A and PT interchange. That is, it is PTA. These things are easy to see. I mean, once you write down these things, it is just you observe the forward equation, backward equation, you get. So if the differentiability of P is assumed at t equal to 0 also, then that what we had seen earlier, but that proof is not all that simple. I mean, may not be simple. That thing which we hold, this expression here, that is, which we have denoted by that star. So this A is called the infinitesimal generator of that birth vector. Like the infinitesimal birth rates, death rates, infinitesimal generator. So the general Markov process theory, the infinitesimal generator plays a very major role. Central role. So theory of Markov process, it has connections with what is called semi-groups. All these the Chapman-Kolmogorov equation in this fashion one can be viewed upon as P of T plus S is equal to PS PT or PT PS. So that is a semi-group of measures. Corresponding to these things, one can attach certain integral operators, and those will be semi-group of operators and so on. But this thing in homogeneous process to be semi-groups, otherwise it has to be slightly different. Yeah, the problem set also I will send perhaps soon. So next class we will start with Brownian motion, one-dimensional space. Brownian motion. So there again we will just be looking at some peripherals. For many of these things to do very rigorously, one should before that do certain things about measure theory on function space, which we are not doing. On spaces of continuous functions and also continuous functions with discrete distance. That is a type of spaces on which the birth-death chains can take value. That is, which allows for certain discontinuities. And that is spaces where sample paths are right continuous and have left limits at every point. So that is the space which includes, of course, continuous space of continuous functions, but that kind of spaces measure theory on that. Especially probability, mainly probability. So if you have no further questions and things like that, we will stop. By the way, your exam will be offline exam, final exam.
Okay.
So give me, I will send a note to that effect. Yeah. So otherwise, we will end the session and we will meet again on Friday. Wednesday. Okay.
Okay. Thank you, sir. Take care.
Thank you very much and take care.